Hello, honors physics students. Today we are going to talk about kinetic energy and the work energy principle. In your Giancoli textbook, it is section 6-3, or in other words, chapter 6, section 3. We briefly had sent the notes before, but we never discussed them, so it wasn't officially assigned before break. We had talked about, we've gone over work and power and potential energy, and so now we're going to talk about kinetic energy for today. All right, so remember that the definition of energy, maybe I'll go ahead and put in present mode for right now. I'll come back and forth. All right, so definition of energy is the ability to do work. It's one of the most important concepts in science that we have. Really focusing on mechanical energy, which we'll talk more in detail about mechanical energy later. But just remember that conservation of energy, the total energy is the same after any process as it is before. That is, quantity energy is a conserved quantity. It is overly simple. It's measured in joules, just like work is. Energy, since energy is the ability to do work, it's measured in joules. Therefore, energy is going to be measured in joules as well. Okay. All right. So the work energy principle, which it does talk about in the textbook on page 142. I did add a page on here to have it break down of how you get the kinetic energy equation. But kinetic energy comes from the Greek word kinetikos. I don't know if I'm pronouncing that right, meaning motion. So remember, kinetic energy is the energy motion, where potential energy we talked about before was energy when things are at rest. Okay. So since an object in motion has the ability to do work, thus it can be said that it has energy. All right, so let's look through this. When a net force performs work on an object, there is always a result from the effort, a change in the kinetic energy of the object, in other words. Kinetic energy is the energy of motion, like I just described. It can be determined by bringing together three basic concepts that we've learned. And again, it breaks it down on page 142, which I attached another slide to that so we can look at that. Newton's second law, which remembers the F equals ma, or F net equals mass times acceleration, whether that's due to gravity or just acceleration. Work, we have the work is equal to the net force times the distance, which can be shown as W equals Fd or W equals Fx. We've also broken it down into W equals max or W equals max, because force is mass times acceleration. You can break it down that way, or W equals mad. If you prefer to use a d instead of an x, it'd be net work is equal to mad or max, whichever way you prefer to write that. And those can be even broken down even further if you use your acceleration equation, and we'll look at that on the next slide here. Kinematics, so knowing our acceleration equation there. Okay, so here's, oops, there it goes. There we go. I'm like, where's that image? Okay, so here's it broken down that page. I just took a picture and added it in here. So to obtain a quantitative definition for kinetic energy. Now, I'm not sure if you guys remember the term quantitative. I do talk about it in my physical science class, but quantitative is a physical property. It's describing using numbers. It's a relationship, so it could be a math equation or a measurement or anything dealing with numbers, whereas qualitative is more of dealing with describing things using words. So this is describing the equation broken down. So we know mass m. Use the pointer thing here if I need it. So mass m is moving in a straight line, okay, with initial speed of v1. Okay, so sometimes we've seen initial speed as VO or VI for initial, or V1 is what you'll see in this textbook. So that's what I tried to use on the problems here. To accelerate uniformly, which remember when we talked about this is back when we talked about constant acceleration equations, those four equations we talked about, okay, to a speed of V2, so to the final speed. So we've seen final speed is VF, or just V, or in this case, V2 is another way to write it. A constant net force, so here's net force is F net, is exerted on it parallel to its motion over displacement D, which in here they use the letter D. You can also use the letter X, is what we've used before when we did kinematics. Okay. And I haven't looked to see figure 6.7. It shows an example of a bus. A constant net force F net accelerates a bus from speed V1 to speed V2 over displacement D, or X if you prefer. So net work done is W net equals F net times D. So that's how you get that equation there. All right, so let's see here. There's that, like we talked about, there's a net work equation I've already discussed. There is the equation that we've learned for Newton's second law. And then here is an equation here to rearrange and solve for a kinematic equation. As described on the last slide, it was based on Newton's second law, work, and kinematics. So already discussed that. So if you can rearrange and solve for a, then you'd have the final velocity squared minus initial velocity squared is divided by 2 times the distance. What do you have it? Use D or an X. That's up to you. And then we can substitute the F net equals MA in here and determine the work done. So like I've said before, W net equals F net times D, or MAD or max if you prefer, if you want to use an X for D, like we've done before. So that if we replace this with the equation up here, we have M times our thing here, our A, times a D. So when you break it down, you end up with this here. W net is equal to M times the final minus initial velocity, and those are both squared, divided by 2. So it is up to you. This is the way it's written. A lot of students, I think for you guys, it's fine if you want to use the 1/2 MV squared. Some students I know with physical science, and they're only, they're freshmen, they really struggle with the 1/2, so they take MV squared divided by 2. This makes it really nice for us because we just plug in 0.5. So this is probably better for you guys to use because you do a little bit more complicated type problems. So W net is 1/2 MV squared. So that's the final velocity minus 1/2 of mass times velocity squared, and that's the initial velocity there. So we define the quantity 1/2 MV squared to be the translational kinetic energy of the object. So in other words, the equation for basic equation for kinetic energy at the base level is 1/2 MV squared, or like I said, MV squared divided by 2. Either way. Okay. All right, so it's one-dimensional motion with a constant force. Okay. Is valid in general for translational motion of objects in 3 dimensions, and even if the force varies. So we'll be using this. Whoops, I don't know why that's in the way. All right, so this can also be written, if you look up here, if K equals 1/2 MV squared, then you have a change in kinetic energy here. You got a final minus initial of 2 types of kinetic energy. So another way to write it is W net equals KE sub 2 minus KE1, which means the second or final kinetic energy minus the initial kinetic energy. So in other words, the change in kinetic energy. This is known as the work energy principle. So another way to state this down below, I have to let it stop the pointer. It keeps showing that up there. The net work done on an object is equal to the change in the object's kinetic energy, which is represented by the delta. Okay, so this page will really help you when you get to the problems and breaking things down and thinking about what is given and what you're trying to solve for, to try to break it down in different ways to solve for the variable that you want. Okay, so if there's any questions on this page, let me know, but I'd refer to this. I did I did add the chapter 6, because this is in chapter 6, book copy of the pages. If you don't have a textbook at home, that is scanned in on, let me escape here real quick, maybe, just so I can show you. This is scanned in right here for chapter 6. So there's the book pages there. You can look through things. This is just 6.3 right now, but it has some different information in there. And then the notes I'll have added on here, along with this video, a screencastify that I'm creating right now. And then I also assigned the book problems as a separate thing, which again, both of these were added previously. Some of you guys might have worked ahead and gotten to that point, but as far as I know, I'd have to look. I know there's at least one student that completed this maybe, but I think that might be it. because we were all working at different paces, there's still some people that still need to turn in the potential energy. So everything that's prior to break was all worth credit in the grade book for a grade. Now, this is the new learning that we're doing, so it's still important to learn and do these problems. I'll talk more about the review activities we did before and what to focus on if you didn't absolutely do anything to do some of that to review your knowledge, because this is something that you will see in college physics. All right, so let's go back to the slides here. I'll go ahead and go to this one. So this is just showing the breakdown, again, kind of more simplified version of it. So we have kinetic energy is this, 1/2 mv squared. All right, net work we know is the change in energy. Now, I'll change this on here so it shows 2 and 1 like it does in the book, but you could use an F and I if you prefer. Usually I see it as a 2 and a 1. So there it is. Okay, same equation on that last page. I just wanted to put that book page in there because it kind of breaks it down really nice in there too. So as far as things here, okay, as far as work, if work is positive, then the object's kinetic energy increases by the amount W. So in other words, the kinetic energy will increase. If the work is negative, then the reverse situation, if the net work done is negative, the object's kinetic energy decreases by the amount W. So that means that the net force exerted on object opposite to the object's direction of motion decreases its speed and its kinetic energy. So it does give an example in the book on page 143 about a moving hammer. A moving hammer strikes a nail and comes to rest. The hammer exerts a force F on the nail. The nail exerts a force negative F on the hammer. Newton's third law, opposite equal but opposite reactions. The work done on the nail by the hammer is positive. Okay. The work done on the hammer, though, is negative. So it shows that example there as far as that. So you can look at figure 6-8 on page 143 if you want a visual of an example of that. All right, relationships. I know before we've done relationships with force and momentum. We know that with force, if you increase the mass, then the force will also increase. Those are directly related. Acceleration is directly related to force, but mass and acceleration have an inverse relationship. We know with momentum that mass and momentum have a direct relationship, as well as velocity and momentum have a direct relationship as well. Okay, so this one we're going to talk about the relationships. The equation is KE equals 1/2 mv squared. So we're relating kinetic energy to mass and velocity. So if you increase the mass, what do you think is going to happen to the kinetic energy? As well as if you increase the velocity, which remember the velocity is squared, so how will that affect the kinetic energy? And which one will be more of an impact? Mass is not squared, but velocity is squared, so think on that. Okay? For both of these, they are directly proportional. If you increase the mass, kinetic energy will go up. If you increase the speed or velocity, the kinetic energy will also go up. So they both increase or they both decrease, depending on the situation, but a different degree. Like I said, velocity is squared, so therefore it's going to impact it more, okay? If you double the mass, you get double the kinetic energy. If you double the velocity, though, you're squaring that, so you'll have quadruple the kinetic energy. So keep that in mind. So this is very important to know and understand as far as relationships. All right, the examples. So I have examples in the PowerPoint, and then I used a separate page. I did the work on paper to make it look a little neater. I went ahead and did it on my blank page sheet that I have used in the classroom before to show and explain the work. So go ahead and try to solve it on your own. As you go through, first step, obviously, with problems is to identify the variables and figure out, okay, what do we know, what we don't know, and what we're trying to solve for. Looking at the equations on page 142 or in these notes will really help you to solve for these. Okay, so this first problem, it's a baseball problem. A 145-gram baseball is thrown so that it requires a speed of 25 meters per second. You're going to assume that's initially at rest. So we're just going to take the values we have here to find the kinetic energy. Remember that the kinetic energy is equal to 1/2 mv squared. We have the mass, we have the velocity, so we're good to go. Now there is one problem. You have to remember, what is mass supposed to be measured in? Okay, mass is supposed to be measured in kilograms. So we're going to have to convert that first. Remember, if you look at your ladder, you have kids help dad because dad can't multiply, or KHD, the base, DCM. So your grams is a base unit, and you're going to have to go up the ladder 3, so you just go backwards 3. So if you take the pointer here, we should be good here. You start here, and you go back 3. You're going to have 0.145 kilograms, okay? And I'll show that on the next slide, so that should be something you should know. Otherwise, speed isn't the right unit, because remember, with this, since energy, its ability to do work is in joules, therefore energy is in joules. To get joules, remember, with work, it is your force and distance. So the equation ends up being, it works out where it's 1 joule is equal to 1 kilogram times meters per second squared. Okay. All right. I might have said that wrong, but okay. So the answer is going to be in 45.3 joules, or 45, because we have to get 2 sig figs here. All right, so I'm going to exit out of this and go to my blank page. I'm going to go to pause this for a second. Okay, so I misspoke there. I think I said 1 joule is equal to 1 kilogram times meters per second squared, but that's actually a Newton. So it's actually 1 joule is equal to 1 kilogram times meters per second. I apologize. All right, so here we go, baseball problem. So we got this, like I said, we converted, and then here's our velocity. We're trying to find kinetic energy. Okay. All right, so here's our equation right here. And we are going to plug in what we have here, half times the 0.145 times 25 meters per second squared. Don't forget, the squared only goes with the velocity. Okay, so then I just plug it in to my calculator or in your head, whichever you prefer, and you get 45.3 joules. And then that will be 45 joules, like I said, 2 sig figs. All right, the other thing it asked for on that slide, I'll go back. What is the net work done on the ball to make it reach this speed? So we know that net force is equal to the change in kinetic energy, which is equal to the 45.3 or 45 joules. So they're going to be equivalent. Okay. If there's any questions on this problem, let me know. That's like the basic kinetic energy problem you can have, like I've done when I teach physical science. Okay, present mode, I'll have to go back and forth. So the next problem is a car accelerating. How much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Okay, so first thing again, we got to think of, what are we trying to solve for? We're trying to solve for net work of the car, accelerating car. It gives us the mass of the car here, and it gives us the initial and final speeds. Okay, so you end up, and I'll show it on the next page as far as that blank page that I'll go to. Your answer ends up being 250,000 joules. Okay, or depending on with sig figs, if you consider this to be 2 or just 1, so you might have 2.5 times 10 to the 4th joules, or 2 times 10 to the 4th joules, or 5th. I apologize, 10 to the 5th. Okay, so hopefully I didn't mess that up on the page, the work page that I have here. So let's go to the blank screen here. All right, gotta scroll down to this problem here. All right, so here's again where I identified. All right, we know from the last problem that, or we've talked about, that the net work is equal to the change in kinetic energy, which change in kinetic energy can be written this way: the second kinetic energy, or final, minus the initial kinetic energy, just like we've done before with change in velocity. We had final minus initial velocity when we did acceleration problems. All right, so then net work could also be written as this part is equal to the change in that's broken down. So then we can break it down again into our KE equations. So half mv squared of our second, our final one, and then half mv squared of our initial. And we're subtracting those to get the net work. Okay. All right, so we plug this in. We have a half times our mass of 1,000 kilograms times our final of 30 meters per second. Okay, and we're going to square that velocity. Don't forget that. So when we do that, we end up with 450,000 joules. And then we're going to subtract the initial kinetic energy. So we have a half times the mass of 1,000 times the 20. And we're going to square that as well. So you end up with 200,000 joules. So when we subtract those, you end up with 250,000 joules, like I said on that, on the PowerPoint notes. All right, and I've already said, and I messed this up, 3, 4, 5. Yep, I messed this up. Let me change this to the 5th power instead. Simple mistake. I knew I'd make a mistake somewhere. All right, so I don't know if there's any, you can put a decimal there if you want. You don't have to. I don't know if there's any questions on what we did to solve for the network by using the change in kinetic energy and breaking it down into the kinetic energy problems to solve for the WNet. Okay. All right. Let's go ahead and go to the third problem. Okay, you can always email me through the school account to ask any questions that you might have, or refer to your textbook, or you can collaborate with other students if you're struggling too. All right, so example 3 of our kinetic energy notes. All right, a space probe of mass that has a mass of 5 times 10 to the 4th kilograms is traveling at a speed of 1.1 times 10 to the 4th meters per second through deep space. No forces act on the probe except those generated by its own engine. The engine exerts a constant external force of 4 times 10 to the 5th newtons, directed parallel to the displacement of 2.5 times 10 to the 6th meters. Determine the final speed of the probe. Okay, so we got our mass, we got a initial velocity, we want to find the final velocity, and we have the F and the D. Okay, so remember F and D, we can use that to find our work, and we can use that and the knowledge here to kind of solve for the final velocity or final speed or velocity. Okay. All right, so our answer ends up being 12,688 meters per second. So let's go to the work document here. It's kind of weird not having a whiteboard, so it takes extra long because I wrote it down and then I just had to type it up. I didn't have this typed up before, so it takes a while. All right, so our space probe, finding final velocity, we have all our identified variable like we talked about here. You can use d or x for your distance value. We know that WNet is equal to FNet times D, or you can even say MAX, if you want to break it down. But since we have F and D, we can use those. There's 2 different ways you write it. So we have our force times our distance, and we end up with a 1 times 10 to the 12 joules for the network. And then just like the last problem, we already know the network is the change in kinetic energy, so we can plug those in because what we want to solve for is that second final velocity. So since we have now the WNet, we have the mass, we have the initial velocity, we can go ahead and solve for that final velocity using this equation that we used on the last slide, or last problem. Okay, so if we break this down, we found network, so we're going to plug that in here, okay, all the way through. And then we have a half times your mass times the final velocity squared, which is what we want to find. So I put that in red so you can see that, minus a half times the mass times the initial velocity squared. So we break it down. So we got 25,000 here, 25,000 here, and I just broke this down a little bit. You might not break it down this much, but I just want to make sure it's clear of what we did. So then I squared this, and I got 121 million meters per second. All right, and then I ended up multiplying these to break it down and get 3.025 times 10 to the 12th joules. Okay, and so in this step, as far as algebraically, you have to get rid of this first because it doesn't have anything to do with what we're going to solve for. So since it's subtraction, we're going to add that to both sides to get it to cancel. So you're going to end up adding that to this value here. All right, and you end up with, oops, let me go ahead and fix this. Let's go ahead and move that so it's a subscript. I knew it again. I missed something. All right, so we have this value here, 4.025 times 10 to the 12 joules is equal to 25,000 kilograms times your final velocity squared. Okay, so to get rid of this, to get v squared by its, or v, the second or final velocity by itself, you divide both sides by 25,000. So when you take this value divided by 25,000, you end up with 161,000. Let's make sure I wrote that right. Seems wrong, but I might be right. Yep, it is. I thought there was 3 more zeros. Okay, so I think I got it right now. All right, so then we have v squared. To get rid of the squared, you're going to square root both sides. Okay, and then you end up with, like I said, 12,688.58 meters per second through space. Or with sig figs, let's see up here, we had 3, 2, 3, 3, so 2 sig figs. Okay, so 1.3 times 10 to the 4th. Did I do that right? Yes, there's 4. Since I messed up the last one, I want to make sure through space. Okay, so if there's any question that I will make sure I will add these images into the PowerPoint. They're not in there now. I'll just screenshot them and add them in as after the slides. So you have those. Okay. All right, go to the next slide here. All right, so unless I'm forgetting something on this, that pretty much summarizes. There's another example on page 144 if you want to look in the book. Work to stop a car, so you can look at that. But it was a very short section, and these are the problems I'm assigning so far on kinetic energy, maybe the work energy principle, using the concepts we just went through on these notes in the Gina Colley textbook. Don't know if I'm pronouncing that right, but page 160. Let me look at that here to see what they look like. 160, number 5 and 6 on that page. And what I'll have to make sure of is that I didn't think about this till now, I have the problems added on here as far as the book pages on here as well. I'll move that up. So you have that. There's a good summary page on 162. There always is a good summary page, breaking everything down. And these are two, probably could have assigned more, but some of these have already been assigned with the work and power and the potential energy problems. So 5 and 6 looks like a conceptual kind of writing out type questions. And then page 162, which is kinetic energy, work energy principle problems. It's 15. You only have to do, there's more problems on there, but 15 through 20 on that page. Okay, and I'll make sure that I add the book problems in there since they're not in there currently, I don't think. I'll have to double check on that. All right. So there is your kinetic energy and work energy principle notes. You should be taking these notes in your, we should already know this, but in your, take out the key terms or key ideas out of here, however you want to do that. And you can put that in your online science journal or your actual journal if you have that. I do have some of them of whoever left them at school. But you can also do that. So you have that in one spot, is what I have on here. Okay. So this is our first time teaching new content. Take them in the online science journal, like I said there, and then these ones. Oh, good. I think that's the right pages. I'll double check. Those are the book problems. That's right. I just reposted what I posted previously because down here is where the unit that we covered before break was on work, energy, and power, and we only covered through potential energy. So I actually had those already down here. So you may or may not have already done those. Again, there's only at least maybe one student that maybe did them. Okay, so all the new stuff, you got your general info stuff, where there's your online science journal. I don't know if I pointed that out yet in this video or not, but there's that right there to use. Okay, remember your submission forms up here. That's how you should submit your work. You can add it on Google Classroom, whether using Cam Scanner or adding it as an image on a Google Doc. Some of you guys have been really good about that. But add it on Classroom to the assignment and then submit through my form so I know that it's done. All right, or I know of a student that email and say, hey, I have this added on Google Classroom, so I know that it was done. But I prefer the homework submission form and not through email as much as possible because it just makes it be in 3 different places. I really just want to check it from here. All right, I appreciate those that have been doing the online work with the review activities. So with that, and there's a daily agenda there to keep track of what we're doing. Here's the new stuff that we'll have. Here's the previous. I should call this, I'm going to rename this the review online learning classroom because that is what it was. Okay. All right. So as far as these, I would definitely do the vocab review for sure. That is one that has reviewed everything we learned this year. So it's a good review to do. I think all the stuff, of course, that I found are really good, but I think this one is a must-do one if you can. And this hockey lesson was pretty cool. I did a video. I think this is the video notes. Only a few people, maybe 3, did the energy wall. It's just a sticky note to just say what you know about energy. So that's a good one. This one I think is a really good one. Potential kinetic energy. We'll do more practice comparing potential and kinetic energy and getting more problems and identifying, is it potential, is it kinetic example. I need to do some maybe potential energy with elastic type problems. I might do that at some point too. But really just doing some The main ones are gravitational and the kinetic problems. This reviewed a little bit with the gravitational Coulomb, so those are just good, like just check to see how well you know stuff. I had both of those and then the practice that went along with that. So there's those if you want to review that. Then we had work and power practice. So if you're struggling on work and power, that was the second practice online. You've already had one practice on it, so it's up to you. The other thing is, I don't know, I need to check to see and update this of who's done the work, power, energy quiz. Remember, we can't do any summative assessments right now, so I'm just really doing more of checks for understanding with formative quizzes. I might try to add some Kahoots. I haven't tried that, I don't think, with you guys yet. It doesn't look like, so we can do that. As far as things here, we have the metric measurement stuff. So the things that we've covered, we have so much on here because we have had this for 3 trimesters. So let's see. Don't remember if I identified. Yep, I did. Okay. A few more. See, we got a ton of metric stuff, didn't we? Try to do that weekly as much as possible. It's just throughout the whole year. So it looks like the OLC ones are the ones I've assigned so far. So review on scientific notation, sig figs. I did a simple one the other day that you should get done. So this is with the new learning. Maybe I need to mark that as new, but new learning started as of, it was either April 13th or 14th, but officially April 14th for our district. So I just wanted you to convert these, or maybe convert them first to pounds, newtons, and meters for each of these, and then write your answer in scientific notation. So those are pretty simple, 3 little problems to convert and write the answer in scientific notation. So if you could get those done and submitted, I haven't looked today to see if anybody's turned that in because I'm working on video notes. All right. Egg jar project, I do have that for more people, not everybody yet. There's not very many. There's only 11 in your class right now. So please get that done and submitted through my form to me on your research. And I don't know if there's any questions on that. I know I relayed a message earlier about reminders. And then, of course, all of these are worth credit. So make sure you get any missing work done. I've been trying to get caught up on missing work for the trimester, and this is the chapter that was on the missing work. So all right, so if you have any questions, I might have to postpone this for a second. I'll add the video in there because it takes a while to load it since it's longer. If you have questions, email me. Office hours are technically 12 to 3. I pretty much work all day anyway on school stuff, so you can always email me any time of day, and I'll respond as soon as I can. I'll get caught up on the missing work, and then I need to give you guys feedback, and I appreciate those that have done the online work, and I hope more of you start to participate or continue and or start to participate with this new online learning because it's things that we haven't talked about before, and I want to make sure you get that knowledge. It will help you depending on what you're going to do as far as college. You most likely, maybe not all of you, will take a physics course, so they'll give you kind of background information on this stuff, kind of base knowledge to use to help you succeed there. So let me know if you have any questions. I appreciate it. I'm going to go and pause and stop the video now, and have a great day.